Good afternoon, everyone, and a warm welcome to this last presentation of today. Thanks for showing up in such a good number. I'm going to tell you something about WinGD's engine and technology advancements for low-carbon shipping, which is one of the very actual topics that we, all of us in this industry, cover as of today. WinGD is mostly known as a main engine designer, as many of you probably know. However, we also offer an extended range of technologies and solutions to support the decarbonization of the maritime industry, not only with engines, but also with other technologies such as hybrid power systems, for example, or digital solutions that help to monitor operations and decarbonize or reduce fuel consumption and reduce emissions overall. In today's presentation, I would like to mostly focus on the what we call future fuel or alternative fuel engines, and you can see a number of engine types that are listed here. We have the XDF LNG engines to start from, which is a very much established solution. On top of that, we also have introduced our XDF-A ammonia, XDF-M methanol, and the XDF-P LPG burning engines. And just to add a latest one to this list, the ethanol burning engines, I will also have a word on that as we continue. So here briefly the agenda. First of all, we would like to look at the latest advancements on the LNG dual fuel engines, where we have introduced a technology called VCR, variable compression ratio, which improves efficiency and reduces greenhouse gas emissions, including methane slip. Then a brief outlook on the ammonia and LPG burning engines, the methanol and ethanol burning engines, and where we stand with that, before we close then with a last slide on our remote monitoring system. So let's start with the LNG dual fuel and this variable compression ratio technology or device that we have introduced to this series of engines. It's actually quite much a groundbreaking technology that we have available for these engine types, because it gives flexibility that has never been there before on any combustion engine, basically. The main target of this clearly is to offer the most competitive solutions in terms of LNG dual fuel. And if we look at some of the main competitiveness parameters, as you can see here in a comparison of a number of versions of our low pressure lean burn autocycle engines compared to high pressure counterpart, you can see that with this latest generation we can offer lower capex because they're still based on the low pressure gas supply system, which is more simple and more cost effective. We can lower overall fuel consumption, which is a surprise to many, but we see the technology is very effective when it comes to reducing fuel consumption. And even if we include methane slip, in terms of greenhouse gas emissions, the solution is very competitive. We have seen a very good market update of this, or uptake of this technology after its introduction. So we have contracted, or our engine builders have contracted almost 170 engines with VCR technology in the last couple of years. First of all, why do we want to adjust the compression ratio on an engine? And in very simple terms, we can say that on a combustion engine, the higher the compression ratio, the higher the efficiency of the engine and the lower the fuel consumption. So there is an interest to maximize compression ratio of an engine. And that's a bit of a compromise, especially on a dual fuel engine that runs on different types of, or two different types of fuels, where on a conventional engine without variable compression ratio, you always have a bit of a compromise in selecting the best compression ratio for operation on either fuel. And that's an advance or an advantage with this VCR system. We can maximize the compression ratio for any kind of operation. And you can see here on this picture an example of the piston position at minimum and maximum compression ratio. So that's the range that we can use to optimize operation in any fuel mode, under any ambient condition, and with any gas quality. So it's an automatic optimization that takes place during the operation of the engine. There are a few main advantages or benefits with this technology. First of all, obviously a reduced fuel consumption, and here you can see two illustrations showing the consumption savings in diesel and gas mode. We're talking about quite significant savings. In diesel mode, what you see here is something like 6 or 7% of fuel savings, so it's quite significant. And also in gas mode, in part load, we have reduced consumption. We have seen reduced methane slip of approximately 30% compared to previous generations of engines, which then result in lower greenhouse gas emissions. And we have also an additional, let's say, flexibility to maximize performance under different operating conditions, as I mentioned. This picture here, or these two pictures, they show how this mechanism looks like. To the left, you can see this knee lever connection feeding oil, like a hydraulic oil, into the crosshead of the engine. And inside the crosshead pin, we have this hydraulic mechanism that consists of something like a hydraulic piston inside the pin. And by controlling the filling level of this lower chamber, we can adjust the position of the piston fully variably during operation of the engine. And that actually happens automatically, so the crew does not need to do anything besides just making sure that the system is activated. But then it runs automatically in the background without any need for intervention. The status of the introduction of this technology is that we have, our engine builders have started to deliver a number of engines. Different types of engines have been delivered from Japanese, but also Korean engine builders now. The system is fully type approval tested by all major classification societies. And I mentioned methane slip before. I would like to put this into a number here. We have seen that this latest 72-bore engine type has reached a methane slip level of 0.7% of the gas consumption. And that is significantly lower than what is typically used as a default factor in European Union or IMO regulations. So very much an advantage here. Then we also have a number of engines in service. The first engine that has been actually converted during a dry dock as a pilot or test installation has accumulated about 4,500 running hours without any failure of the system. That has been a very good operational feedback. And with this, we were confident to state that with VCR, the engines actually become the most competitive LNG dual fuel engines in the market. So that was the first topic. Let's move on to the XDF-M methanol burning engine, which is another type of engine that we have developed and introduced to the market. Here is a summary of reference projects that we have. So those are contracted projects. You can see we have totally contracted 76 sets of engines, and you can also see that many of them are of a large bore type, so 82 or 92 centimeter bore types, which are typical applications on large container vessels. A brief overview of that methanol system, and as with many other engine types here, we actually base this fully on the diesel base engine. So the diesel engine, conventional diesel engine, is the basis, and then we add this purple system that you see on this illustration here, which is the methanol injection system. And here just a few examples of components. First application actually was on a 92-bore 10-cylinder engine, a big engine with more than 50 megawatt of power output, powering a 16,000 TEU container vessel. Here just a few illustrations of the components of the system and how that looks like in reality. Talking about test results in terms of performance here have been very positive. We have seen that our performance predictions were fully met, so fully in line with our performance predictions and guarantees. Interestingly also, we see that in methanol mode, the consumption is actually lower than of a diesel engine. So it's about 2% lower consumption, which comes from a better, or let's say a lower NOx production during operation on methanol, which allows the engine to be somewhat more fuel optimized compared to a regular diesel engine. Also here, two different engine types have been delivered, 82-92 bore. As I said before, performance targets were fully met, and first vessels are now in operation with very good feedback so far. And the portfolio extension is ongoing, so by end of next year we will have engines delivered in the range of 52-92 bore, so basically covering our full bore size range of two-stroke engines that we offer. And now moving to ethanol as fuel, and that's actually very closely connected to the methanol engines. Ethanol as fuel is something that we have seen in the recent, say, year, has grown massively in terms of interest. So we do receive a lot of inquiries about ethanol as fuel, and much of that comes from the fact that ship owners that have ordered methanol-fueled vessels, they realize that green methanol is at this moment and in the foreseeable future is not available in, let's say, within reasonable quantity. Ethanol, though, is in a way a very similar fuel. It's also an alcohol, same as methanol, and in many aspects it's very much comparable. While the biggest difference from an engine point of view is a difference in heat value. So the quantity of fuel that you store in the tanks, but also burn in the engine, is somewhat lower compared to methanol because it has a higher energy density. The ethanol engine is fully based on the methanol design, so there is no major design difference in that, and I think it's important to understand that the engine can operate on both fuels, so it can run on ethanol or methanol, and that is what we believe the key enabler to have a faster uptake of these types of engines because you simply have a much better coverage of fuel availability. And we do expect first engine deliveries possible from 2027. Ammonia engines, another very interesting topic which we believe in the long term is going to be one of the major solutions in the market, simply because ammonia is a carbon-free fuel. And the production of ammonia is therefore a lot more simple and cost-effective compared to other green or synthetic fuels, such as green methanol. For ammonia engines, we offer a number of engine types now from 52 to 82 bore up to 50 megawatt of power. And the engines that you see here are available in our program, and they can be ordered at our licensees. Again here, a list of reference projects. We have contracted 32 engines, ammonia fueled, of 3 different engine types, and you see here a selection of different ship types with application of ammonia fueled engines. Obviously, many of them are actually ammonia carriers, and that also makes sense because you then use the cargo as a fuel also. Here are a few selected performance results. We have seen from the testing that engine efficiency is comparable to a conventional diesel engine, so we have a very high efficiency also when running on ammonia. Combustion stability is very good, and maybe that is one of the key findings, that ammonia as a fuel is very well suitable for a two-stroke engine. A lot of people were concerned that ammonia, which has let's say, is more difficult to ignite, it has a lower flame speed compared to other fuels, that this would create problems when using it as a fuel on a combustion engine. But what we have learned is that these properties actually fit very well to a slow-speed two-stroke engine, because we have a very slow engine. Having a low combustion speed is actually beneficial and fits very well to the requirements of a low-speed two-stroke engine. Also, the potential for greenhouse gas reduction is very big, so assuming that you run on a renewable ammonia fuel, the reduction potential is more than 90%. The remaining percentage comes from the pilot fuel that is used. And even that could be replaced by a biofuel source, which means that in that case the reduction is more than 90 up to close to 100%. And also in terms of emissions, we have measured very good positive results with low slip rates of ammonia, so low unburned ammonia levels in the exhaust. And also NOx emissions are lower, about 40 or 50% lower compared to a diesel engine. The status of that introduction is that the first of these engines was tested here in Korea by HHIMD and delivered to the shipyard. It's currently being installed. The second engine is under testing, and we will conduct type approval testing on that engine very soon. Performance predictions are fully met. As said, the performance results were very good and promising for all future deliveries also. Same with emission test results. Then a few words on the XDF-P, the LPG burning type. And here I have to say these engines are fully based on the ammonia engine design. The intention here is that we focus very clearly on the market segment of gas carriers, so MGC, VLAC, VLGC type vessels, and that is why we have these two engine types, 52 and 62 bore, available in our program. So it's the same injection system as what we have on the ammonia engine, and what we are targeting is to offer a very simple upgrade from LPG to ammonia at some point in time. We see many of these ships are expected to carry LPG as cargo for the first few years. After a few years, we expect that, or if the owner has any plans to change cargo from LPG to ammonia, we want to enable a very simple conversion of the engine to also go upgraded for ammonia operation. And that is possible because the engines are already designed as ammonia engines in the first place. So this is expected to give maximum flexibility for owners and operators to adjust their selection of fuel according to the cargo they carry. So that was about the engine part, and now I have one last slide on our white system, as we call it, just to give a little bit of an impression of what we do besides all the engine design. White is our digital platform. It's called the WinGD Integrated Digital Experts. It's basically a data collection and monitoring system that also analyzes data on board, then also sends reporting data ashore. And the idea here is that you basically have a system that monitors engine operation. It gives advice on any kind of adjustments or improvements that should be done to optimize efficiency, reduce fuel consumption, but also if there is something that doesn't operate as planned, and in order to avoid any unplanned downtime or repairs, the system can already give predictive indications if something is not going well. This system, we see, gives a lot of extra information to, let's say, the operating crew on board, to the ship managers on shore, but then also to WinGD, as far as we are allowed to have the data from the owner, because the data belongs to the owner. But if we're allowed to receive that data, we can also help with troubleshooting, for example, or operational advice. Again, with one target to reduce fuel consumption and reduce emissions. And with this, at the end of my presentation, I would like to thank you all for your attention.